Welcome to today's video on energetics. Don't forget that you've got the worksheet in the description below, so make sure you've downloaded it before you watch this video. I'm going to go through a ton of questions on energetics that will hopefully give you an overview of what you're doing well at and what you might still need to work on before your exam. So let's get going. Let's start by having a look at the equations in this unit and the equations that are in SL energetics to start with. So the first one, and in fact the only one of these equations that is in the data booklet, is this one here, which is Q equals mc delta T. Just to show you, in the data booklet you'll find this in table 1 under topic 5, which is Q equals mc delta T. So it exists there for you, but you still need to know what all of those letters mean and what units are required for that. So for this one in particular, we use this normally when we're measuring the temperature rise of a liquid or of a solution, and then we want to know how much heat energy was transferred to that solution. So normally what you're measuring here is you're measuring the change in temperature, the delta T, and we measure that in Kelvin. So the change in temperature in Kelvin goes here. Now for everything else, it relates to the thing that you're measuring the temperature change of. So if I'm measuring the temperature change of water, then also the C is going to mean the specific heat capacity. Heat capacity of the water, and that is your 4.18 joules per gram per Kelvin. And this also you can find in the data booklet in table 2. So specific heat capacity of water you'll find here in table 2. You'll notice that it gives it in 2 units, in kilojoules per kilogram per Kelvin and also in joules per gram per Kelvin. So just to be aware what units you're using for the mass will affect what units you get for the energy overall. Just make sure the combo that you're using is all good. So the M, as we were just saying, stands for the mass, which I'm going to say is in grams because of the unit here. I took the one in grams, which means the heat energy, or the Q, is going to be in joules. Equally, I could have had this in kilojoules and this in kilograms, and that would have also worked just fine. We'll look at some example questions with this one in particular, because people get confused as to which numbers go where, and I'll show you what I mean by that in a bit. Normally, once we have the heat energy that's transferred to the liquid, I then want to know the delta H, or the enthalpy change for that reaction or the combustion or whatever you're doing. So the delta H is normally measured in kilojoules per mole. That's your definition of any enthalpy change. Units are kilojoules per mole. And to take that, we take our Q, which is the heat transferred from the previous step, divided by the moles. And this moles could be the moles of fuel that you burned, or it could be the moles of the limiting reagent. It really depends on the scenario. So we'll go through an example in a bit. Okay, now these last two, I'm not gonna lie to you, I don't know these equations, because every time I'm given a question with these delta H's and formations and combustions, I will think about the problem and whether it's subtracting products from reactants or reactants from products. So for some people, it helps to memorize these equations, but actually for most, and if you're solving the more difficult problems, you really want to avoid relying on these equations too much because they will not be helpful to you in every single scenario. So here, the top one, you've got your delta H for the reaction. You'll notice this weird little symbol up here. It's a theta, Greek theta. Looks a bit like a Saturn. And this just means standard temperature and pressure, which is your 273 Kelvin and 100 kilopascals. Okay, and what this equation means is that if you're given delta H for any reaction, you'll take the sum of the delta F's, which is your enthalpy change of formation for the products, minus the enthalpy change for the delta for the formation of the reactants, and then overall you can work out the enthalpy change for that reaction. If you're given combustions instead of formations, then it flips around just because of the direction of the arrows and becomes reactants minus products. So just to be aware that they flip around and they can change. But let's do some examples in a bit and we can see how you would utilize these inside a question. Okay, let's look at some multiple choice questions on endo versus exothermic. This is a really, really common example and is worth taking your time to think about what the question means rather than rushing into it. So here they've given you an equation and then they've asked you whether the reactants are more or less stable and then whether the reaction is endo or exothermic. So we're really solving kind of two parts to this. This part, the exo-endothermic, is a bit easier to solve because they've given you the delta H. If the delta H is negative, then if the delta H is negative, then that means that the reaction is always going to be exothermic, which means it's giving out heat energy to the surroundings. Now the reaction profile for an exothermic reaction, so if you've got reactants and products, and the energy looks a bit like this. The reaction pathway is at the bottom. And then the energy profile looks a bit like this for an exothermic reaction. So the products are more stable, the reactants are less stable. So overall, I want less stable and exothermic. And so overall, D is the correct answer here. For number 2 here, what can be deduced from this reaction profile? You can see this is essentially the same question, just written in a different way, and you'll find a million of these that look almost identical from different exam seasons. So here you can see that the reactants are still less stable, they're higher in energy, and the reaction is exothermic for the same reason as it was before. Okay, so let's get started on using the equation Q equals mc delta T. This is often something that people find tricky at both HL and SL, so it's definitely worth having a look at this equation in preparation for your exams. So here, they've given you a question about working out the enthalpy change of combustion of methanol. They've given us the mass of methanol in grams, and they've also told us that the heat released increased the temperature of 50 cm cubed of water and the temperature rise that they observed. So hopefully from that kind of information, you should be forming a picture that looks a little bit like this in your brain. So you've got the spirit burner at the bottom, burning off the methanol. So the methanol is down here, but this could be any fuel. In this case, we've got 0.230 grams of methanol was used. And then up top here, we've got water, and there's 50 cm cubed of the water. They said that it went from 24.5 to 45.8 degrees, which is an delta T of 21.3 degrees C, which equals 21.3 Kelvin overall. So this is going up, which you would expect if you're doing combustion, by 21.3 Kelvin overall. Okay, so when we've got this, we know that we're going to have to use Q equals mc delta T, hopefully, because they've given us enough information. So let's have a look at that equation and what we need from it. So if I've got Q equals mc delta T, remember that we need to make sure we're using the values that correspond to the thing that's changing in temperature. So in this case, we're changing the temperature, or we're measuring the temperature change of the water, which also means that I'm going to take the specific heat capacity of the water. It means that I want the mass of the water because I need to work out the heat transferred to the water. Because what most people will do here is they'll see this mass and they'll put it straight into this equation here, but actually that is incorrect in this case. So let me show you what you should be putting into this equation. So the Q equals the mass of the water, remember, so the mass of the water is 50 grams. They told me it was 50 cm cubed, and I assume that 1 cm cubed of water weighs 1 gram. So this becomes 50 grams of water. We're going to times that by the specific heat capacity of water. Remember that 4.18 that you can find in the data booklet right here. And we'll keep it in joules per gram per Kelvin. And then the change in temperature, which we worked out at the top, which is my 21.3 Kelvin. So if we calculate that, you should get Q equals 4451.7 joules overall. And this is the heat energy transferred to the water. Okay, so we're kind of halfway there, but they want an enthalpy change. They don't want the heat energy transferred. Enthalpy change, remember, normally measured in kilojoules per mole. So I'm going to need to make some changes here first. So enthalpy change, delta H equals your Q divided by the moles. Okay, so we have worked out Q already, this 4451.7 joules. And then we need to divide it by the moles. Now in this case, because they're doing enthalpy of combustion, it's the moles of fuel that are burnt. So I need to work out the moles of fuel, the moles of methanol that are in that 0.230 grams. So this, I need to do moles equals mass divided by the formula mass of the methanol. So this is 0.230 divided by the formula mass, which is 32.05. If you calculate that, you get the moles to be 7.176 times 10 to the minus 3 moles of methanol that are burnt. So what I'm really doing is I'm saying how much heat energy was transferred to the water when the fuel was burning, like how much of that fuel burning did I need to burn to get that heat rise. So here, if we calculate this overall, you end up with 620,000 joules per mole. I've rounded this to 3 sig figs because every single number in the question is to 3 significant figures. So that's a really good ballpark if you're not sure how many significant figures to round to at the end. You might also have this as 620 kilojoules per mole, which is also fine. Now, before I move on, both of these answers will not get me the full 4 points. They will both get me 3 points overall. Because this is a combustion reaction and the temperature rise is increasing, you need to remember that this is an exothermic reaction, which means that I need to make sure, I'm going to do it in red because it's aggressive and something that we're always going to forget. We need to make sure that we're putting the negative sign in front of that final number. Now there's nothing in the calculation that really tells you that you need to do this, so it's just something that you need to be really aware of in yourself, and you need to check your final delta H values to make sure that they make sense. The other way that you might be expected to use Q equals MC delta T is for the enthalpy of a reaction. So normally a neutralization or a displacement. So a reaction that's happening in one reaction vessel. So here it says 200 centimeter cubed aqueous solutions. So we're thinking about what this looks like. So both of these beakers have 100 cm cubed in them. One contains 0.1 molar of sodium hydroxide, and the other contains I lost a zero there. 0.010 of sodium hydroxide, 0.010 of hydrochloric acid. They are at the same temperature to start with. When the solutions are mixed together, so that means that overall we now have this reaction mixture, this is now 200 cm cubed, and it's a mixture of those, the acid and the base. If I'm taking the temperature of this, they say that the temperature increases by y degrees C. I'm going to put a lid on for the same reason. You might even coat this in some kind of insulator to stop heat loss to the surroundings. So they're asking, what is the enthalpy change of solution in kilojoules per mole? So if we go through the same thing as we did last time, the Q equals mc delta T. So here, we always start with the delta T, because if we know what we're measuring the change in temperature of, then everything else kind of becomes easy. So the delta T is definitely Y, because remember, Y in degrees C is the same as Y in Kelvin. The specific heat capacity is saying we use the specific heat capacity of water, so that's 4.18. And the mass is going to be the mass of the thing we're measuring the temperature of. So I'm measuring the temperature of this vessel here, the one with everything mixed together. So the mass of that in the liquid, it says assume the density is 1 gram per centimeter cubed. So that means that the mass of this is going to be 200 grams overall. So right now I've got 200 times 4.18 times Y, and that's going to give me the Q, which would be in joules. So for this one, they want kilojoules per mole. So to get this into kilojoules, it's going to become 200 times 4.18 times the Y divided by 1,000, and that would be the Q in kilojoules, and that's the answer there. Okay, now they're saying what is the enthalpy change in kilojoules per mole. So to get the kilojoules per mole, that's going to be delta H equals Q divided by the moles. So Q is this expression that we've just written, and we need to divide through by the number of moles. Now often the question is like, which moles do I use? Do I use the moles of NaOH, the moles of HCl? Do I use them both combined together? And in this scenario, you always use the moles of the limiting reagent, the one that's going to run out first. Unless they tell you something different in the question, assume you're taking the moles of the limiting reagent. So that means that I'm going to take, they're both the same in this case, and the equation balances 1 to 1, because if you've got NaOH plus HCl, then it becomes NaCl plus H2O. So this balance is 1 to 1, so I don't need to worry about limiting reagents and things like that, because they're both going to balance perfectly. So here, to get my delta H, I'm going to need to times this by the moles, which is going to be 0.10. So I've now changed this, it's not Q anymore, this is delta H. And so the expression that represents this in my options here is B. Lastly, you often get a lot of questions in this unit about what causes issues with the numbers that you're evaluating. So heat loss to the surroundings and incomplete combustion, so lack of insulation are really big ones in this unit. So for this, it says the enthalpy of combustion is determined by taking a known mass of tap water and burning ethanol. What will lead to the greatest error in the final result? So this is saying that all of these are errors, but which one is most significant? So the most significant is normally heat loss to the surroundings. So that's what I am hunting for here. And there it is in option B. You're assuming all the energy from the combustion will heat the water. So if we went back up to that example at the top, if we look at this diagram here, we're saying that all of the energy from that flame, from the methanol burning, was used to heat up the water, which is definitely not correct because you've got all of the air around it, the universe around it, which is also being heated up as well. Okay, so let's have a look at the definitions for enthalpy of combustion and formation and how you can articulate those using an equation. So firstly, these values for enthalpy of combustion and formation you actually will find in the data booklet. So if you go all the way to tables 12, you'll find that there's enthalpies of formation here in table 12, and then in table 13, this whole table is on enthalpies of combustion. So just make sure that you know those values are there in case you ever have to use them in an exam question. So here we'll find these in table 12 and 13 in the data booklet. So the first thing says, deduce the equation for the standard enthalpy of combustion for phenol. So if we're doing enthalpy of combustion, this is the enthalpy change when 1 mole of a fuel is burnt in excess oxygen when everything is at its standard states at room temperature and pressure. So what we're going to do is we're going to make sure that my C6H5OH is on the left-hand side of this equation. And it's the enthalpy change when 1 mole of this fuel burns. So I need to make sure that this number here stays as a 1 in front. When I balance it, I'm not allowed to change that 1, it has to be a 1. So it's burnt in excess oxygen, remembering that oxygen is diatomic, to produce both CO2 and water, which are your products of complete combustion. Now, all of these need to be in their standard states at room temperature. So for oxygen, you should know that's a gas, CO2 also a gas, and then water is a liquid at room temperature and pressure. The last step for this is that I need to balance it. So the carbons, I need 6 CO2 to balance the carbons, and then I'm going to need this 6 hydrogens here, so I need 3 waters to balance that. And then for my oxygen, overall that is 7 O2. So this balances nicely. This could be worth 1 mark, maybe 2 marks in certain exams. So just make sure that you can write these equations out. Just for completeness, we're also going to have a look, oh, this is a typo here, at the standard enthalpy of formation for phenol. So if I asked you to do the enthalpy of formation instead of the enthalpy of combustion, how would that be different? So the enthalpy of formation, remember, is when 1 mole of the substance is made from its elements in their standard states under standard conditions. So what's different here is that we start with the right-hand side. So in this case, we're making phenol. And the important thing here is that I'm making 1 mole of phenol, and I need to keep that as a 1. I can't change that number overall. So it's made from 3 elements, carbon, hydrogen, and oxygen. Now you need to add that these 2 are both diatomic in their standard states under standard conditions. And to balance this, we've got 6 carbons needed, and then I need 3 H2s to balance out those 6 hydrogens, and then I just need half an O2. So we can use fractions in these equations in order to balance them to maintain this 1 here. You cannot change that, otherwise you're changing the definition of what the standard enthalpy of formation means. So this one is a solid at room temperature, same as above. The hydrogen is a gas, standard conditions, and then oxygen is also a gas at standard conditions. Hess's law is often one of the things that SL students in particular find really challenging in energetics. So for this question here, they've given you a reaction which they want you to work out the change in enthalpy for, and they've given you delta H formation values. Now this means that I can use that equation that is at the top of this page here, this first one, where the delta H of any reaction is all the delta H formations minus the delta H formations for the reactants. So products minus reactants. So let's go back to the equation here. So if we were to have a look at this, we're saying delta H equals the delta H formation for the products minus the delta H formation for the reactants. So this one, the products in this case is my CO2 and my 2SO2. So that's minus 390 plus my minus 290, but I need to times that by 2 because there's 2 of them here. Okay, so that's all of my products. And then I'm going to subtract the reactants, which is my 110 from my CS2 plus 3 of the oxygens. Oh wait, so the oxygen they didn't give me. So remember that the enthalpy change of formation for an element is always going to be 0 because it's already an element in its standard state. So this doesn't count, so I'm just going to leave it like this. And that is perfect. So overall, this gives you minus 1080 kilojoules per mole. And that means that your answer is D. Now you may recall at the beginning of this video I said that I didn't really know these equations, and that's because I kind of solve it by trial and error and by drawing a Hess's cycle whenever I'm given one of these. So let me kind of show you what I mean by that. So if I rewrite out the equation here, I'm going to skip the state symbols because I don't really need them in this case, 2SO2. And now what they've given me in this question is they've given me the enthalpies of formation, which means that for all of these compounds, they've told me what the enthalpy change is when I go from the elements to the compound. So I can draw the cycle here. Going from the elements to the compounds and adding in the enthalpy changes that they gave me in the question. So for CS2, this number is 110 here. For oxygen, remember that this one doesn't have an enthalpy of formation, like it's already its element in standard states. And then the CO2, this is going to give me the minus 390, sorry. And then the SO2, this is minus 290 times 2. Okay, now the reason that I find this easier is that what we're doing in a Hess cycle is we're going from reactants to products. So we're always going across from one to the other. So in this case, I'm going to go in this direction instead. So I'm going to go from left to right overall. And then any arrows which are facing the wrong way, I'm going to flip around. So for example, let me show you this one here. To go this way, between the CS2 and the elements, this number is going to become minus 110. And then this one's going the right way, this one's going the right way with my highlighted arrow. And then all I have to do is to add up all of the arrows on the route. So that becomes minus 110 plus minus 390, and then plus minus 290 times 2. And you add them all together and you get the same number overall. So if you're not sure about the equations overall, you can solve things using a different route by just building your own Hess cycle rather than relying on memorizing the equations. In terms of problem solving, you could also be given a question like this, which is asking you to work out the enthalpy change for a reaction. And then they gave you some other reactions and some equations to go from. Now, if you've got equations to go from, then what I would recommend doing is using a different strategy whereby you try and combine these equations like you do in simultaneous equations in math in order to generate that final equation that you're aiming for. So if I look at this first equation here, this one, number 1, and I compare it to my highlighted equation, I can see that it's similar in that both of them have this aluminium oxide on the right-hand side. but the difference is that there's a 2 in my final equation. So what I'm going to do is I'm going to times this whole equation by 2. If I look at the second one, if I times the whole thing by 2, sorry, then you end up with 6 over 2 or 3, and then the 4 here. So if I look at the second one overall, then you can see that what is similar is it's got this manganese oxide here, and it's got the manganese here. You can see that in both cases there's a 3 in front, so I'm definitely going to need to times this one by 3. But what I'm also going to do is I'm going to reverse the reaction. So I'm going to put a negative in front of this, and I'm going to change the arrow to being a reverse arrow. So now all of these become 3 overall. Now what's cool about this is that if you basically just add both of these equations together, you would get the highlighted equation that I've got written here. So in order to get the enthalpy change, all that I need to do is to add all of these numbers together. So overall, that should give you D, because I need 2 of the minus 1670, and then I'm going to add that to 3 times plus 520. This is another really similar one. They've given you an equation to aim for, and then they've given you equations underneath to utilize. So if they've given you the equations underneath, what I'm going to do is I'm going to compare what's similar and what's different. So I can see that there's carbon dioxide in my equation, there's oxygen in my equation at the top, there's more oxygen, there's also some water in the one at the top, and then there is this butane here, but nothing else. The carbon, the hydrogen, that's all got to cancel out because it's not in my final equation that I'm aiming for. So because your oxygen appears in both of these places, I would really recommend that you leave it till last and just assume it's going to work itself out, which 99% of the time it magically will do. So let's have a look at the carbon dioxide in this first one and compare it to my equation. So I can see here that I'm going to need to times this by 8 to get these to all be 8 overall. And that means that my CO2 is now the same as the one on the top. In the second one is the water that I'm looking at. Remember, I'm leaving that oxygen until the end, and that means that I need to times it by 10, and that's going to become 5, and that's going to become 10. So overall, you can see how my equation is kind of building out. And then in this last one, if I compare it, I can see that I've got my butane in both, but it's on the other side. So in this case, I need to flip the equation over. So I'm going to make it C4H10 goes to 4Cs plus 5H2. And this is now kind of minus Z overall. And I can also see, compared to the one at the top, that this is 2 butanes overall. So I'm going to need to times this by 2. That gives me 2 of this, and then that will give me 8 of the carbons, and that will give me 10 of the hydrogens. Now, if you've kind of been like paying attention to the numbers here, you'll notice that I also made 8 carbons here. So that means that these will cancel out overall, and that means that your equation overall, when you push them together, you would get the one at the top. So all that I need to do is to add all of these things together. So it becomes 8x plus 10y minus 2z. So the answer is C overall. Okay, so question 9 is kind of cool in that it's actually the part B from question 5 that we did earlier, where we worked out the equation for the standard enthalpy change of combustion for phenol. So that's kind of the starting point for this question, and you can see I've written it here already for us. In this question, however, they gave us some information about the enthalpy changes of formation of carbon dioxide and water, and then they asked us to calculate the standard enthalpy change of formation of phenol. So because all of these are formations, I'm assuming I'm going to have to build a Hess cycle which encompasses the elements of each of these compounds and try and connect them up somehow. So I'm going to solve it kind of one step at a time. So underneath here, to join everything together, I'm going to put the elements. Now there's no reason why I have to actually like list out what these are for the calculation, but I will show you here just for the sake of it. So really what you've got is you've got 6 carbons. Carbon just exists on its own, and then we've got 3 H2, and then we have got how many oxygens overall? That is 7 O2, so we've got 7.5 O2s on both sides of the equation. So if you were doing balanced equations, that's how you could balance all of the equations that this is connecting to. So let's have a look at what we've got and what we've been given. So I've been given the enthalpy of formation of carbon dioxide and water. So enthalpy of formation, remember, is forming that compound from its elements. So this one is minus 394, but I'm making 6 of them. So I have to make sure I times that by 6. For the water, it's minus 286 kilojoules per mole, but I'm making 3 of them, so I'm going to times it by 3. If I'm connecting up to the oxygen, remember this arrow doesn't need a number on it, the value is 0, because to go from oxygen to oxygen is just going to be nothing because there's no change in bonding or anything, so 0 kilojoules per mole. And then the enthalpy change of formation for the phenol is actually the number that we're looking for here. Like, this is the one that I want. So that means that I'm missing this delta HC at the top. So maybe it says using information from table 13, I'm going to hunt down that number and hopefully it exists in there. So this is still open at table 13. So this is really the wrong way around and not helpful at all. But you can see there's phenol here in the solid state, and the enthalpy change of combustion is minus 3053. So let me add that onto here. So this becomes minus 3053. So now the whole thing is connected apart from this arrow that I don't know, the one that I'm trying to work out. So what we do is we're looking at the direction. So this is like the starting point, and this is the end point of the arrow. So we're going to go in an indirect route from one to the other. So the direction, we're going kind of up this way and then across to the original side. So like normal, any arrows that are going the right way, I'm just going to leave the numbers as they are. If the arrow is facing the wrong way, I'm just going to flip it so that all of the arrows go in the circular direction that I want them to. So overall, I can see that this arrow here is going in the right direction. It's going up and around, as is my water formation here. This combustion arrow, however, is going in the opposite direction. It's not going the right way. So I need to flip this arrow round, and that becomes a plus 3053 kilojoules per mole. So then, to get the overall delta H formation, I just need to add together all of these numbers, which is the minus 394 times 6 plus minus 286 times 3, and then plus the 3053, and that overall should give you minus 168 kilojoules per mole. Now, this question you can't really solve using that products minus reactants thing, because they've kind of asked you to solve one of the side arrows versus the arrow at the top. So this one you kind of have to either write equations or draw a cycle. It is a really good way of testing whether you actually understand how to do this or not. It is a tricky one. Okay, now that marks the end of the Hess's Law stuff, because I know that's hard, so I spent a bit more time on that today. And this is the last part, which is bond enthalpies, the last part of the SL, I should say. So bond enthalpy values you can find in the data booklet. back on table 11, bond enthalpies and average bond enthalpies at 298 Kelvin. Be cautious that this table 10 with the covalent bond lengths looks really similar. So this one is table 11 for the bond enthalpies. So just so that you know that's there. Here they've given you an equation and they've asked for the enthalpy change in kilojoules using the bond enthalpy data given below. So they actually gave you the values here because obviously you don't have a data booklet in the multiple choice questions. So for bond enthalpies, all of these values just mean that the energy required to break 1 mole of the bonds. So for each of these, I need to know which bonds exist. So I would recommend drawing out in like a sketch form the bonding that exists in the species that you've got in your question. So carbon monoxide, I know is a triple bond. If you didn't know that, there's a big clue because there's the only one that's in the table here. And then you've got the water, which is like this. So overall, I've got 2 of these, and then I've got 3 of the oxygens, and then I've got 2 of the carbon monoxides, and then I've got 4 of the waters. So this is really going to help me to work out how many bonds I've got and what things I need to times together with each other. So this one, the 414, overall there will be 8 of these bonds because there's 1, 2, 3, 4 here, and then there's 2 of them overall. The same with the oxygen, that's my 498. I've only got 1 here, and then I'm going to times it by 3 because there's 3 of them. So these 2 processes are both endothermic, they're bond breaking. So endothermic, remember, is positive, and you should know that bond breaking is endothermic. That should be a fact. And then we're going to the other side, which is, I've got the carbon monoxide, this 1077, a lot of energy, it's a triple bond, and that's times by 2 because I've only got 2 of those. And then in the water, I have got 1, 2, so that is 463, 2 times 4, which gives me 8 overall for the water. These are going to be made, so they're bond making. If it's bond making, then this is exothermic. So the numbers on the right will be subtracted from the numbers on the left. Now I know there's equations here that you can do like reactants minus products again, but as long as you're thinking about which one is bond making and which one is bond breaking and which one should be positive or negative, you're just essentially like adding the 2 numbers together, and that's going to cause you far fewer problems overall. So of the options that I've got here, the correct one is this one here, C, because you can see overall that I've got this, which is the same as what I've got on this side, and then subtracting, because they're exothermic, the same as what I've got here overall. Another type of question that you get for this is about which equation corresponds to the bond enthalpy of a bond overall. So bond enthalpy is just about breaking the bond. So the 2 electrons that are being shared in the covalent bond, one is going to one of the elements and one is going to the other one. It's not being split unevenly to make ions or anything like that. You're just taking the compound, or the bond in this case, and you're making the 2 individual atoms. So in these 2 cases at the top, you'd be reforming bonds because you'd have to reform the hydrogen or reform the iodine bond and have to take that into consideration. Bond enthalpy is just about the breaking. If I just break it into the 2 pieces, what does it look like overall? Okay, let's have a look at this last one. Why is the value of the enthalpy change of this reaction less accurate than calculated from standard enthalpies of formation? So this is asking about the problems that are involved with bond enthalpy data. So the biggest problem with bond enthalpy data is that all compounds are different, and so when we take bond enthalpies, we take an average value an average value of many different compounds, and we assume that like all compounds do similar. So it's a good model for us to like start with, but you wouldn't make any like hardcore predictions using this. So in this case, the value is, they are average values for many compounds. And that is all for the SL stuff. So here are our HL equations that we've got for this unit. There's only 3 of them. So this first one is about entropy change, so delta S under standard conditions. And the units for entropy are, you've got joules per Kelvin per mole. So all of these actually are in the same units, joules per Kelvin per mole and joules per Kelvin per mole. This one is not in the data booklet, so it's definitely something that you just need to know. And in actual fact, like for the most part, like if you're not sure whether it's products minus reactants or reactants minus products, you should definitely just go products minus reactants. You're more likely to be correct more often. You might get a few wrong, but generally speaking, products minus reactants is a great starting point. So that's our equation for working out the entropy change for a reaction. This one here, this delta G equals delta H minus T delta S, is actually in the data booklet. It exists in that first table. Just to make you aware, it exists here. It's the only one for this unit that exists for the HL content. So, I did not mean to do that. So here, this one exists in the data booklet. You have got the delta G, which is your Gibbs free energy change. And that is measured in kilojoules per mole. You've got delta H, which we talked about in the SL stuff, which is also measured in kilojoules per mole. This T here stands for temperature, which is measured in Kelvin, like normal. And then this is your entropy change, which here we're going to have to use in kilojoules per Kelvin per mole. Notice how the units kind of changed. On this side it's in joules per Kelvin per mole, and then over here we need to use it in kilojoules per Kelvin per mole in order to cancel out those units in the equation. So just be aware that the units of entropy are not super consistent and are likely to be why you make mistakes in utilizing these equations. Okay. So this last one, the delta G, so if you're working out the Gibbs free energy change for a reaction, you can also do the Gibbs of the products minus the Gibbs of the reactants, and that will give you a value for the total Gibbs free energy change and allow you to be able to predict spontaneity. The units for all of these are in kilojoules per mole, so that is a good starting point. Okay, so let's have a look at Born-Haber cycles. In this question, they've kind of constructed one for you already, but you should be pretty familiar with how to construct your own, should a question ask you to do that also. So in this one, you've got a Born-Haber cycle for sodium oxide. I tend to start in this bottom left-hand corner. This arrow here in the bottom left is normally a delta H formation. And that is normally followed by atomization. So if you look here, you can see that the sodium is going from solid to gas. So that's the delta H atomization for sodium. And then in the next step here, you can see that it's the oxygen that's changing. And this is actually the delta H atomization for oxygen. So it going from its standard state as molecular oxygen in gaseous form to just oxygen atoms in the step above. Next one, we have got the change here is the Na going from Na to Na+, so this is an ionization energy for the sodium, first ionization energy. And then in this one here, you've got oxygen going from O to O2-. So that's actually an electron affinity where it's gained an electron. And actually it's the electron affinity, like the first plus the second electron affinity for oxygen, because it's gained 2 electrons, not just 1. And then lastly, on the right-hand side, you've got the lattice enthalpy here. So just make sure that you know exactly what all of those things mean and you know definitions for them also. So in this question, what they're asking is for calculate values for the following changes using section 8 of the data booklet, and then they also gave us some atomizations here which will hopefully come in handy later. So for the first one, you can see it's going from half an O2, so if we compare that to what's going on in our equation, half an O2 going to going to O2 minus. So really they're asking for this process here. So half an O2 going all the way up to O2 minus. So with regards to oxygen, this is really your atomization for oxygen. And as well as that, let me move this over to the other side. You want to move? As well as that, it's your first and second electron affinity for oxygen. So those are the two things that I'm going to need to add together in order to work out this value here. So I'm going to need the atomization for oxygen, which is given here, this 249, plus the first and second electron affinity. And they gave me a clue as to where to find this in the question in section 8 of the data booklet. So you can see here I highlighted earlier in section 8, you find the electron affinity in the top right hand corner. Sorry, it's oriented badly. But you can see that the numbers up here are minus 141 for the first electron affinity and then plus 753 for the second one. So let's add those together. So this becomes plus minus 141, which is that first one, and then plus 753. And overall, that should give you 861 kilojoules per mole. And that's for that whole step, going all the way from the O2 all the way to the top of my Born-Haber cycle of the O2 minus. And then we're going to do the same thing for the sodium. So here, the sodium is going from Na solid to Na plus. So it's actually making the same journey, Na solid going all the way to Na plus. But you can see this time I've only got these two. I've got the atomization plus the ionization. So the atomization I'm going to take from here, this 107, and I'm going to add that to the ionization for sodium. So first ionization energy lives in the top left hand corner. So for sodium, that's 496. So we're going to add those together, 496, and that gives me 603 kilojoules per mole. And that is the end of this part of the question. Okay. Now the next part of the question says the standard enthalpy of formation of sodium oxide is minus 414. Now the first thing I'm doing is I'm chucking that on the diagram so that I know which thing it relates to. So minus 414 is going to go right here. Minus 414. That's the enthalpy of formation. Done. Determine the lattice enthalpy of sodium oxide in kilojoules per mole using section 8 of the data booklet and your answers to D part I. They also gave me some other answers to D part I if I'd had a really bad day. But you can see actually these are really similar to our answers, so that actually gives me a lot of reassurance that I did a good job. If your answer is really different from these numbers, you've probably made a mistake. You can always just use these numbers in the question. Nobody will penalise you, but they're definitely not 100% correct. So they want us to work out the lattice enthalpy of the sodium oxide. So that is this one here, the lattice enthalpy. So let's look at what we've got. So the lattice enthalpy overall, the lattice enthalpy overall is the value going all the way from here to the top. So what I can do is I can look at this cycle and I want to take a different route. So rather than taking the route from here to here, like I would do if I could and they'd given me the number nicely, I'm going to go this way instead. Okay, now let's have a look at this. So this arrow here, I need to flip the other way around. So this is going to become a plus 414. So it's going to go 414. Let's move this a second. So we're going to do delta H lattice. So 414 is just coming from that arrow being flipped so that it's facing upwards, which is the same way as my lattice enthalpy arrow. And then I already worked out what some of these journeys are on my in part A of the question. So for the sodium, you can see if I was going from Na to Na+, I've already worked out that that is 603 kilojoules per mole. But in this case, it's 2 Na. So I'm going to need to times this whole thing by 2. I'm then going to add on the oxygen. The oxygen is, I'm going from a half O2, and this is a half O2 also, so this equation is identical to what's happening in my Born-Haber cycle. So I'm just going to add on that 861. So what we're essentially saying is that we have this formation, the plus 414, because I've got to flip the arrow to make them all face the same way. And then I'm taking this journey from the 2Na up to the top, which I worked out in part A, and then from the half O2 to the O2 minus. So this one here is my 603 times 2, and this side here is my 861. And those all combined equal the lattice enthalpy for sodium oxide. And in this case, the answer is plus 2481 kilojoules per mole. So check that you get the same answers as me. Feel free to write it in the box. You should be getting a positive value for lattice enthalpy. We work it out as being endothermic in IB, so the energy required to break apart that solid ionic lattice into the gaseous ions overall. Okay. Other questions that can be asked about lattice enthalpy in some capacity is this comes up a lot in multiple choice, where we're talking about what has to be a characteristic of an ion which has a large lattice enthalpy. So lattice enthalpy is breaking apart that ionic lattice. So what you're really thinking about is like which ions are going to stick together best. And the strongest electrostatic attraction always comes from things that are really highly charged and really small. So we call that a high charge density. So you want small and highly charged. So the answer in this case is D. You want it to be little but highly charged. This type of cycle with enthalpies of solution, hydration and lattice enthalpy are pretty new to the syllabus, and there's not a ton of questions on them. So this is something that is really worth revising, especially if you're aiming for one of the top grades. Just in case it does come up in the exam, it's probably something you are a little bit less familiar with. You can find values for enthalpies of solution and hydration and lattice in the data booklet, and you will find these in tables all the way past some of this other stuff. Tables 18 will give you the lattice enthalpies, and then you've got enthalpies of solution in table 19, and then in table 20 you find the enthalpies of hydration. So there's actually like a ton of information here. So this is tables 18, 19, 20. You will find information about these different enthalpies. In terms of definitions, make sure that you can define all of them in terms of an equation. It's a really useful thing to be able to do. So let's have a look at the question. It's saying which equation represents the enthalpy of hydration. I recommend for all three of these that you have an idea of how to write the equations for each one, and that will help you to know what the definitions are. So enthalpy of hydration is the enthalpy when 1 mole of gaseous ions form 1 mole of aqueous ions in solution. So the enthalpy of hydration in this case is B, but you do also have examples of solution and lattice in this, which is kind of why I picked this question. So C, this one here, going from a solid ionic compound into gaseous ions, this is the delta H lattice, which we saw actually in our Born-Haber cycle in the previous page. And then D, you've got a delta H solution. solution, where you're going from the ionic compound and you're dissolving it in the maximum amount of aqueous solution to make Na plus and Cl minus. Check out these definitions in a bit more detail if you are not sure. This question here is a longer answer, like a paper 2 style question for this content. I couldn't find one that was really suitable in my past paper questions, so actually just found this one online and kind of tweaked it a bit, so this one is a bit weird. The lattice dissociation enthalpy of magnesium chloride is 1240 kilojoules per mole. Using table 20 in the data booklet, calculate the enthalpy of solution of magnesium chloride. So as normal, I would suggest that you took the one that you're trying to calculate and you put it at the top. So this means we need to write an equation for enthalpy of solution for magnesium chloride first. So magnesium chloride, enthalpy of solution means we're starting with it as a solid ionic compound. We're dissolving it in the maximum amount of water that we can to make it saturated. And then you're making Mg2 plus aqueous and 2Cl minus aqueous. And we're doing this to like infinite dilution. So this is the one that I'm trying to work out. This is the enthalpy of solution. What they've given me is they've given me the lattice dissociation enthalpy. So that is going from the solid, this one here, to the gaseous ions. So you've got Mg2 plus as a gas, and then 2Cl minus as a gas at the bottom here. So if I connect these up, this is my lattice enthalpy, and this is plus 2540 kilojoules per mole to break up that solid into those gaseous ions. So I'm hoping that table 20 is the one with the hydration enthalpies, because that's going to help me to go from the gaseous ions to the aqueous ions, and those numbers are the ones I need to complete my Hess's cycle here. Okay, so let's have a look at table 20. Oh, we're still there, magic. So the magnesium is 1963, and then the chloride is minus 359. So let's add that onto our diagram. So for the magnesium, you've got minus 1923. That's right, yeah. 1963. Oops. 1963, and then for the chlorides you've got minus 359 times 2, because I've got 2 chloride gaseous ions going to 2 chloride aqueous ions. So now my Hess cycle is complete, and that means that I can work out the enthalpy of solution for magnesium chloride. So if we take these arrows here, we're trying to go from here to here, but we're going to go in this indirect route all the way around. And actually, all of my arrows right now are facing the right direction. So what we're going to do is we're going to just add together all of these numbers. So we're going to take my plus 2540 plus minus 1963 plus minus 359 times 2. And that overall should give us minus 101 kilojoules per mole. Actually, this one definitely, I've miscalculated here, should be minus 141 kilojoules per mole. Sorry about that. So let's move on to entropy, which is has the symbol S or delta S if we're talking about change in entropy. You'll find the values for entropy all the way back in table 12 over here. So these are values for entropy that are given to you by the IB. So knowing that they exist is always a good start. So these style questions are really common in the multiple choice, asking about changes in entropy values. What you're really looking for is, are you having other more particles on the left or the right? And also the changes of state between left and right. So if you've got a negative value for delta S, this means that you've got decreasing disorder, or that it's getting more organized. So I'm either looking for fewer particles, or fewer gaseous particles in particular, or a general changing of state towards becoming more ordered. So that means it's going from a gas to a solid, or a gas to a solid, or a liquid to a solid, it's becoming more ordered overall, will give me a negative value for delta S. So in this top one here, you can see that there's 3 particles on the left and only 2 on the right. So this is definitely becoming more organized, less chaotic on the right-hand side than it was on the left. So I think this is probably the right answer, but let's check the rest of them. In B, you're going from a solid to a gas, so this is definitely becoming more disordered, so you would expect a positive delta S for this one. In the third one, C, you've got two gaseous particles going to 2 gaseous particles, so this one I have no idea, I can't predict it. It won't be a lot in either direction. And then in this last one here, I've got gas going to gas, so no changes of state, but I'm going from 2 particles to 4 particles. So that's definitely becoming more chaotic, so I would expect a positive delta S value for that one. Okay, last little section. So Gibbs free energy and spontaneity. So Gibbs free energy is just a mathematical model that we use to predict spontaneity, and this is the type of questions that come up about Gibbs generally for the IB. Just to complete my section, the values for Gibbs you will find also in table 12 of the data booklet. So if you need to use them for that equation that we talked about at the beginning, then you find them in table 12. In terms of multiple choice questions on Gibbs, they're really only asking about the relationships between delta H and delta S and how that relates to spontaneity. So it says the delta H and delta S values for a certain reaction are both positive. Which statement is correct about the spontaneity of this reaction at different temperatures? So the equation delta G equals delta H minus T delta S, if both of these are positive, then what's correct about the spontaneity? So facts that you need to know is that spontaneous reactions, the delta G will always be negative. So if your delta G is negative for these reactions, then that means that overall I need this to be negative. Now you can see in this case, there's no guarantee that this is always going to be negative or always positive. It depends on the relationship between the delta H and the T delta S. So what you've got here is the delta H being positive. I want this number, if I want spontaneity, I want this number to be as small as possible, and then I want this number here to be as big as possible, because I want to be subtracting the biggest number away from it to make it the most negative or the most spontaneous. So the way that we describe that is that we say that the way it's going to get bigger is that the T, the temperature, is going to change. So making that bigger is going to make it more spontaneous. So it will be spontaneous at higher temperatures, but not at lower temperatures. Now question 20 is an almost identical question, but what it does is it asks you to explain, in terms of delta G, why a reaction for both delta H and delta S values are positive is sometimes spontaneous and sometimes not. You actually get a point here just for saying that spontaneous is where the delta G is negative. So make sure that you're stating the obvious in your questions. And then we're really talking about the relationship, and the way you should write about this is that, like, if delta H is less than T delta S, then delta G will be negative, and therefore it will be spontaneous. But if delta H is greater than T delta S, then delta G will be positive, and therefore not spontaneous. So therefore, higher temp is more spontaneous. So I really recommend you just use inequalities to describe this, because it's really about the relationship between those two factors, and it's only the temperature that can change in a reaction. Like the delta H and the delta S are set if you know what the reaction is and it's done, you can't change it. It's only the temperature that can change. This is a continuation from question 9 that we finished up a bit earlier, where we worked out the delta HF, the enthalpy of formation of the phenol already. So actually in this question, they went on to ask you to calculate the delta G, the standard free energy change of phenol at 298 Kelvin. So this is utilizing your delta G equals delta H minus T delta S. So we actually already worked out that this delta H is 168 kilojoules per mole. And then we need to put the rest of the stuff into this equation. So the temperature they gave you in the question is 298 Kelvin, and we're going to times that by the entropy value, which they also gave us as minus 385 joules per Kelvin per mole. But you need to remember in this case that actually we need to divide this number by 1,000, because it needs to be in kilojoules per Kelvin per mole to balance out the other units in this equation. Changing this unit is the most common mistake in this type of question, and you get a point for it, like just knowing that the entropy needs to change units. So overall this delta G is minus 53.3 kilojoules per mole. In the next question, they ask determine whether it's spontaneous and give a reason. So yes, spontaneous, because the delta G is negative, and that in this particular example will pick you up a magical 2 points. Okay, now that is all for energetics. If you have any more questions or you have another topic that you want me to look into, then please just leave a comment below and I will get back to you. See you soon.